Hi, this is Sung, and I'm your online maths mentor. And in this episode, what we're going to be doing is looking at another example involving simple harmonic motion. This time, this example involves when you've got speed as a square function, right? Basically, when you've got speed or velocity expressed as a square function, right, with respect to your displacement. Not with respect to time. In this case, it's with respect to displacement. And when you've got something like this, oftentimes you'll have simple harmonic motion as well. So let me go through the relationship that you'll need to know. The square of the velocity, right? So the square of the velocity will be, oftentimes, if it's simple harmonic motion, it will be n squared outside of a squared minus x squared, right? How do we get that? Okay, how do we get the velocity squared is equal to n squared outside of the amplitude squared, so minus the displacement squared? Well, essentially, this is basically the thing that sets up the relationship. So let's have a look at here. Let's have a look at this. We know that in a simple harmonic motion question, you have a trigonometric function, right? So for this trigonometric function, you've got a, which is your amplitude of times a trig function. Let's say it's a cos function there, right? Now, if you've got then, right, the velocity, which is the derivative of your displacement, your velocity is equal to negative a sine nt plus c. So in other words, you differentiate to get your velocity. Then let's see what happens when we square the velocity. When we square the velocity, we get that, right? The negative will disappear. It'll just be that, okay? From this point here, let's see what we do, right? So from this point here, I want you to recognize that the square of a sine function using our trigonometric identity is going to be sine squared alpha, which is equal to 1 minus cos squared alpha. Got it? Cool. So when that's the case, we can go from this line to this line, right? So the square of the velocity is equal to n squared a squared. So let's bring the n squared out the front, and then this sine squared can become a 1 minus cos squared, right, to the product of an a squared. So that's what you get. Now, if you have a look at this, what you'll find is that all of that is our displacement again. Do you see that? So there we have it. The velocity squared is equal to the amplitude minus the displacement, the square of the amplitude minus the square of the displacement times your constant, all right, n squared. All right, so fantastic. There we have it. That's something else that we know about simple harmonic motion. Now let's have a look at this example. In this example, you've got the speed, which is v centimeters per second, of a point moving along the x-axis is given by v squared equals to 36 minus 6x minus 2x squared. And then it says, prove that the particle moves in simple harmonic motion, find its period and its amplitude. Cool. All right, so you got v squared is equal to 36 minus 6x minus 2x squared. Okay, so that's your starting point. Now, here's what I want you to know, right? We're gonna move from there into acceleration. And on your reference sheet, you will have this. Okay, that'll be on your reference sheet. In fact, I've got a reference sheet here. It will be at the top of page 4. Okay, so on your reference sheet, this will be on the top of page 4, right? And what I want you to notice is that when you've got a v squared type function, right, you can actually go from a v squared type function, right, where the subject is v squared, to acceleration through this, right, which basically says we halve our v squared function and then we differentiate with respect to x, and that'll give us the acceleration. All right, so let's do that. So we know that v squared is equal to 36 minus 6x minus 2x squared. Halve that, and that's going to be 18. All right, so basically go from there to there by halving, everything, and then we can differentiate that with respect to x, and we're left with our displacement. So let's do that. So d dx of half of v squared, and that should be equal to, let's differentiate all of that. The 18 will disappear, we're left with -3, and then we differentiate that, it's minus 2x. Got it? So in other words, our acceleration is going to be, and we bring out the -2, x plus 3 on 2. Got it? Cool. Fantastic. So acceleration is equal to -2 outside of that. Now here's what I want you to know. If we look over here, do we see that we've got something that very much resembles what simple harmonic, the relationship between acceleration and displacement for a simple harmonic motion type scenario, okay? And we can actually translate that over here, which means that the -2n is going to be represented by the n squared, and all of this is going to be represented by the x, but I want you to notice something. I want you to notice this plus 3 on 2. Now what does that actually do? What I want you to notice is that that is the center, right? Or that actually informs us as to the center of the simple harmonic motion. It basically tells you where the center of the oscillation is, right? So what we should have is a particle that moves, right? If that's 0 and that's -3 on 2, that is basically where the oscillation is going to take place, somewhere around there. So in other words, hang on, let me come around this way. So basically, you've got a particle that basically oscillates back and forth about that point there, which is -3 on 2. Does that make sense? Okay, cool. So let's work out what n is. So you've got n squared is equal to 2, n is equal to √2, which means that your period is equal to, what is it, 2 pi on n, which is equal to 2 pi on √2, which is equal to, now what's that? So it's √2 pi, okay? So our period is going to be √2 pi, okay? What does that mean? Okay, we worked out what the period is. We now got to work out what the amplitude is. All right, now I'm going to do something very sneaky here. We know that v squared is equal to 36 minus 6x minus 2x squared. Okay, so I'm actually going to factorize that. Okay, so let's have a look. So v squared is equal to 36 minus 6x minus 2x squared. I'm probably going to take the 2x, so the -2 out. Okay, and we're left with x squared plus 3x minus 18. All right, when we factorize that, we get v squared is equal to minus 2 x minus 6, or plus 6 x minus 3. Does that make sense? Cool. Now from here, we are going to work out what x is when v equals to 0. So when v equals to 0, what's happening? So when v equals to 0 is going to be at the extreme points of your oscillation. It's basically where it turns back around. So a particle is going to go from the center to the extreme point. It has to stop, so in other words, it's stationary for a brief moment, and then it has to go back all the way around until it gets to the other extreme point. It stops temporarily and then comes back around. So the V0, where V equals to 0, will be very telling. It'll tell us where the extremities of the oscillation are, okay? So if V equals to 0, what we get is 0 equals to minus 2, x plus 6, x minus 3, divide both sides by -2, we can get rid of the -2, and at this point, x equals to -6 or +3. Now let's have a think about this. If that's the case, what that means is that you've got -3 on 2, which is -1.5. You've got 3 on this side, -6 on this side. What is the distance between the center and the extreme point? it's basically 3 plus our 1.5, which is 4.5. And it's also going to be 4.5 on this side. Does that make sense? That's going to be your amplitude. So your amplitude is going to be 4.5. Your amplitude is going to be 4.5. Your period is going to be root 2 pi. And that's how you do these sort of questions. Okay? So just have a look at that. See if you get it. And then I will see you on the next episode. Thank you very much for watching. Bye.